Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Okay, today I will continue electric circuit 1. We will discuss about the chapter 7, FET DC analysis or FET biasing. So in this chapter, we will learn some configuration like in BGT. We have a fixed bias, self bias, voltage divider, and then we also have a depletion type and enhancement type MOSFET. So I will divide this learning video into two parts. The first one I will discuss about the fixed bias and self bias configurations, and then the second part is voltage divider, to the depletion type MOSFET, and also enhancement type of MOSFETs. And then I will summarize all the configurations. And then this one is optional. You can learn by yourself about the combination network design and P-channel, GFET, and etc. So you can learn by yourself, because this is the important thing is the configuration of the FET DC biasing. Okay, so for the FET, the relationship between the input and output is nonlinear due to the square term in Shockley equations. So in FET, as you know that FET is voltage control current source. So the current between the drain to source is controlled by the voltage between the gate to source. So we can, in this biasing, we will often to draw the relationship between the drain current to the gate to source voltage, or ID versus VGS, to the FET configuration. So the general relationship between the DC analysis of FET amplifier, the first one is IG is near to 0. Why? Because of in FET, like in MOSFET, we have the gate. This is the gate terminal, and this is the source terminal, and then this is the drain terminal, and we have a silicon oxide here. This is the silicon oxide here, and silicon oxide is insulator, so there is no gate current through the channel between the drain to source. So it means that here IG is nearly 0 here, because there is no gate current into the channel. And then the ID, drain current, is similar to the source current. And for the GFET and also the depletion type of MOSFET and MESFET, we use the Shockley equations. So the ID, the drain current, is IDSS, saturation of drain current, multiplied by 1 per VGS per VP quadrat. So this is the relationship between the input and output. You can see from here that this one is constant. This is the constant, and VP also the constant. Okay, here, so we can control the ID by changing the VGS. Okay, so it's why the FET is a voltage control current source, because we control the ID using the VGS, voltage between the gate to source. And then for enhancement type of MOSFET and MESFET, the following equation we can apply. ID is equal to K multiplied by VGS minus VT quadrat. Okay, so this is the configuration of the fixed bias. We apply the gate to source voltage, or VGG, here, and then we connect to RG, or gate resistance, to the gate of the MOSFET. Okay, something like that. And then the configuration in figure 3 includes the AC level of VI, input voltage, and output voltage here, and then coupling capacitor to prevent the DC current through the input. So it will prevent the C1, it prevent the DC current here, so the DC current didn't go to the input voltage or the output voltage. Okay, then so it's like the coupling capacitor is open circuit for the DC analysis and low impedance for the AC analysis. And RG here also, this is we put RG here to prevent the input AC go to the ground here. So the AC signal will go to like this one. So this is the AC signal. If we didn't put RG here, the gate resistance, so the AC signal will coming to the ground, because in AC analysis, all the DC bias will be a ground. So AC will go to the ground and then will be appears. So we will disappear. So we will prevent the AC signal goes to the ground. So we put the RG here in high impedance of RG. Then, because the insulator, this is the silicon oxide here, is very large, so the Ig is equal to 0. And then, if we use the Kirchhoff law like this one, we can use the VRG, the voltage between voltage drop in the RG is IGRG, because the Ig is equal to 0, near to 0, and RG is unlimited or is high impedance, so VRG is 0. So we can draw the VRG is 0, so we can replace the circuit into the DC analysis like this one. So we didn't put the RG again here. And then we can see from this figure that the voltage between the gate to source is depend on the VGG here. Okay, so it depends on VGG. If we increase or decrease the VGG, the VGS also increase or decrease. It depends on the VGG. Okay. And then, okay, in here, the fixed bias for FET biasing, we connect negative bias to the VGS. So we can apply the Kirchhoff voltage law here. So we can get that means VGG minus VGS is equal to 0, and then VGS is minus VGG. And then because the VGG is fixed DC supply, this is the fixed DC supply. Fixed DC, so we call this configuration by fixed bias configuration, and then we can know the drain current by using the Shockley equation like this one. Okay, because of VGS here is constant, so the ID also constant here. Okay, so here we can see that from this circuit, we have to plot the IDQ or key point of these circuits. Okay, and the first one, how to define the key point of this circuit. The first one, we have to plot the FET characteristic here, like this one. So when the ID is equal to 0, VGS equal to VB, this point, and then when the VGS is equal to 0, the ID is IDSS. This I discuss or I explain this procedure in last subchapter when I discuss about the FET. So if you forget about how to plot the blue lines like this one, the device characteristic, you have to see my previous explanation about the basic of FET. Okay, and then the third point is if IDSS is per 4, so the VP is per 2. So we can draw, this is the FET configuration here, or FET characteristic. And then how to define the key point? We have to, in the fixed bias, we have to plot the black line or the network. This is the device characteristic, and this is the network characteristic. Yeah, this is very easy for fixed bias because we only have to know what is the minus VGG. So minus VGG is VGS key. So if you put, this is the minus VGG here, and minus VGG is fixed like this one. So we can plot because like this one. So this one between the device and network characteristic is the key point. So this is the key point. We plot here, this is the ID key, and this is the VGS key. Okay. So the intersection between the network configuration or network characteristic and device characteristic is key point here. Okay. So we can easily move the key point to the right part or left part by changing the VGG. If we increase the minus VGG, so it will be go to the left side. If we decrease the minus VGG, so it will become to the right side. And then the ED key will change if we change the value of minus VGG. Okay. And then we can, after we find the ED key here, we can find another parameter like VDS. VDS you can see here. Here this is the VDS, voltage between the drain to source here. So VDS is plus VDS plus EDRD minus VDD is equal to 0, or VDS is VDD minus IDRD. Okay, so we can find RD by specific value, ID from the key point, and VDD by specific value. We can calculate the VDD. Okay, and then recall that Vs is equal to 0 because the source is directly connected to the ground like this one. And then so VDS is equal to VD minus Vs. So the VD is VDS plus Vs or VDS plus 0. So VD is equal to VDS. And also VGS, VG means Vs, VG is VGS plus Vs, or VGS plus 0. So the VG is equal to VGS. Okay, this is for fixed bias. Okay, so this is the example. Determine the following of the network. We have the EDS. The device characteristic EDS is equal to 0 is 10 milliampere, and then VP is minus 8. And then RD is 2 kilo ohm, RG is 1 mega ohm, and then the minus VGG is 2 volt here. This is the VGG. Okay, the question is VGS key, ED key, VDS, VD, VD, VG, and VS. The first one is VGS key. Yeah, we can solve it easily because the VGS key in fixed bias is minus VGG. So it's become minus 2. And then ED key is IDSS multiplied by 1 minus VGS per VP quadrat. And then a 10 multiplied by 1 per VGS is minus 2. So this is minus 2, and VP is minus 8. So this is minus 8. So we can get that 5.625 milliampere. And then VDS is VD minus VDD, sorry. VDD, okay, VDD minus IDRD. VDD is 16 volt here, and then ID is 5.625 milliampere, and RD is 2 kilo ohm. So we got that VDS is 4.75 volt. And then VD is VDS is 4.75 volt, VG is VGS is minus 2 volt, and Vs is equal to 0. So we can also draw from the device characteristic like the figure 7.7 here. Okay. From figure we can find that VGS key here is 2 volt. We can solve it by mathematically, like in here. This is mathematical approach. And then we can use graphical approach like this one. The first one, we have to plot the device characteristic like in blue line here. This is the blue line. And then we plot the circuit characteristic by red line like this one. And then the intersection is the key point. We can see here ED key is around 5.6 milliampere, and VGS key is minus 2. Okay. So this is a quite extendable. So between the mathematical analysis and graphical is very close. We can see here VGS key is minus 2, ED key is 5.6, and then VDS is 4.8. Yeah, very close. VD is 4.8, VGS is minus 2, and VS is 0. Okay. And then the second part of the bias configuration is soft bias configuration. You can see from figure 7.8, we didn't put any bias voltage in between before the RG or gate resistance. So we connect RG to the ground, but in this case we connect source resistance to the ground like this one. Okay, and VRS, you can see from this is the Kirchhoff law here. VRS is IDRS, okay, like VRT is IDRT. So from the indicated flows, we can see that from this one, this is using the Kirchhoff flow, minus VGS minus VRS is equal to 0. So VGS is minus VRS, and VRS here is I minus IDRS. So we can see that VGS is a function of the output current. So if the output current changes, the VGS also changes. And then the magnitude is not fixed here because we didn't put like a bias voltage before the gate resistance, like in fixed bias. So in mathematical solution, we can see obtained by substituting equivalent 7.10 here to the Shockley. So in Shockley, ID is equal to IDSS multiplied by 1 per VGS per VP quadrat, and then we replace VGS by minus IDRS. So we can get this equation. And then if you can see, you can put more detail about this equation, but we can write in the simple approach that in this equation we will find that it is the ID quadrat, and then constanta multiplied by ID, and then K2 is equal to 0. So from here, this is like the quadratic equation. So we have at least two roads here. We can see that this is the different roads or similar roads. So because of this have 2 points here, so we can draw the network configuration, network characteristic by put this one like when VGS is equal to 0 or ID is equal to 0, so VGS is equal to 0 because the VGS is minus IDRS, so we can get 1 point here. And then another point is we can put that ID is equal to IDSS, and then VGS is minus IDRS, so VGS is minus IDSS RS per 2. Okay. So we can see here, when the ID is IDSS per 2 here, the VGS is minus IDSS RS per 2. And then we can also solve another, after we find the key point, after we find the device, the circuit characteristic, we draw between the 2 points and we got that key point here, or ID key. And then we can solve another parameter like VDSS, VDS, because of VRS plus VDS plus VRD minus VDD is equal to 0. So the VDS is VDD minus VRS minus VRD equal to VDD minus RS minus IDRD. And then if we use the ID is equal to IS, so VDS is become VDD minus ID RS plus RD, and then Vs is IDRS, Vg is 0 volt, and Vd is VDSS plus S, or VDD minus VRD. Okay, so this is the example. Determine the following for the network. We have the network IDS device IDSS is 8 milliampere and Vp is minus 6. And then we have VRS 1 kilo ohm, RG is 1 mega ohm, and RD is 3.3 kilo ohm, and we have the VDD 20 volt. The question is VGS key, ID key, VDS, Vs, Vg, and Vd. So we can determine the gate to source voltage by determining that VGS is equal to minus IDRS. And then for example, we choose the ID is equal to 4, so we can obtain that VGS is minus 4 multiplied by 1 kilo ohm, because RS is 1 kilo ohm, we got that this is minus 4 volt. So we can define the characteristic of circuit by plot 2 points. The first one is when VGS is 0, ID is 0. And then the second is when the ID is 4 milliampere here, the VGS is minus 4. So we have a two point here. And then we can check another point, but 2 I think is enough. And then we can draw the circuit characteristic like this one. Okay. Then we have to draw the device characteristic by using the IDSS and VP like in previous chapter. So we can draw the blue line like this one, okay? And then for ID key, the intersection between the blue line and black line is ID key. So ID key is 2.6 milliampere. And then VDS, question number 3, VDS is VDD minus IDRS plus RD. So we insert the VDD, IDRS, and RD. So we got that VDS is 8.82 volt. And then Vs is IDRS, ID is 2.6, and NS is 1 kilo ohm. So Vs is 2.6. Vg is equal to 0, and then Vd is VDS plus Vs. 8.82 volt plus 2.6 volt, 11.42 volt. And then Vd or Vd is equal to VDD minus IDRD is 20 volt minus 2.6 milliampere multiplied by 3.3 kilo ohm. We got that similar number, 11.42 volt. Okay. And then we can change the key point by changing the RS like this one. We can get that when the RS is 100 ohm, ID is 4 milliampere and VGS is minus 0.4. We have the key point here. The key is equal to 6.4 milliampere. And then if we increase the RS until 10 kilo ohm, we got that key point here. So the key point when the VGS is equal to minus 4 and ID is equal to 0.4 milliampere. Okay, so this is another example you can find by yourself how to determine the following for the common gate configuration. It's similar with the previous problem. Okay, so I think for the first part I will finish right now, and then in the second part we will continue to finish for finishing the DC analysis for GFET. That is a voltage divider, depletion type, enhancement type, and also another maybe important subchapter in this chapter. Okay, thank you very much for your attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.